All right, so we're starting. Today's all about, actually, let me, you can write down that table as we're going. It's about exponential functions today. 5.3 is all about exponential functions. First off, what is an exponential function? When I say that phrase, do you know what an exponential function even is? Let me ask you a question. How about x cubed? Is that exponential? Answer is no, actually. That's not exponential. Now, why not? That's got exponents. Why is that not exponential? It's not. In fact, I'm going to go to a fresh screen if that's okay. I'll come back for the table in a minute. Y equals x cubed is not an exponential function. It's not what we mean when we talk about an exponential function. Why not? What is an exponential function then? Or x squared, same thing. X squared's not. Anybody know what an exponential function is then? Yeah. Yeah, x itself is in power. Not just that it has powers. Lots of things have powers. But that x itself has climbed up there into the power zone, like 2 to the x. That's exponential. So exponential. This making sense then? So today is all about exponential functions, which means x itself has climbed into power. And there's a big difference between a regular function and an exponential as far as how fast it goes. What do I mean? I don't know if you ever hear the news and they'll go, blah, blah, blah is growing exponentially. They mean it's just rocketing up, right? Exponential growth, it rockets up like that, super, super fast. Now, I would think if I was you and when I was first new to this kind of material, I thought, what do you mean they're all fast? I mean, like x squared, that's a U shape, that's going up real fast. And you're saying that's not exponential, and you're making this big deal out of exponential like it's way faster? Is it? Is that true? Is it way faster? Well, yeah, it is. Let me show you. Let's actually do a table and see how much faster exponential functions are than even something which is somewhat fast like x squared. If you're just at 1, he's just at 1, right, for x squared. Plug in 1 with me. Y equals 1 squared. If you go to 2, what is 2 squared? 4. You go to 3. 3 squared. Whoop, not 3. I wrote 3 to the 9th. 3 squared is 9. Anyway, let's jump down to 10. If you go all the way to 10, how high is the function at 10? 100. It's at 100, right? So that means if you're over here at 10, he's way... Well, see, 100 is way off my screen. That's pretty high, right? Over at 10, he's up to 100. Let's try the other guy. Let's try the exponential. He's way more powerful. So if you just do 1, what is he? 2 to the 1. I just put the 1 here. 2. That's just 2. It's not a big deal. Do a 2. 2 to the 2. That's 4. Whoops. Let's do a 3. Yeah. It's 2 to the 3rd. That's 8. It's not that big a deal. What are the numbers doing?
Double.
They're just doubling every time, aren't they? Right? Because this is 2 once, 2 to the 1. This is 2 twice. It's another 2. This is 2 to the 3rd. 8, right? Let's jump down to 10. What is 2 to the 10th? Do you know what?
100.
What is it?
Double 100.
No, 2 to the 10th power?
Oh,
1024.
1024. What was the other one? 100. He blows it away. He's 10 times as high. 1024 compared to just 100. Way bigger. See, it's just rocketing up, isn't it? That's what they mean when they say such population or whatever they'll talk about in the news is growing exponentially. They mean it's rocketing up. And literally, that's actually a good example. We're going to talk about exponential growth in 3 ways, and this is what this section is all about, exponential growth. And 3 different ways. We're going to look at tables, first off, like I just made a table here. We're going to look at tables and how tables lead to exponential functions. We're going to look at graphs. Well, that's not exponential. This would be the graphs of exponentials. And then we're going to look at equations for exponentials. So we're going to want to be comfortable with tables, graphs, and equations for exponentials. So we're starting with tables. Like, how do you know, if you're looking at a table like this, if that data is exponential data or not? How do you know by just looking at a table whether the data in that table is from an exponential function Or they're going to also give me the option of linear or neither.
I don't know.
So it's exponential, it's linear, or it's neither on that.
Well, right.
Yeah, doubling. Yeah, remember what happened? It's good thought. Yeah, look back at the one we just did. See the exponential one over here? Look at what those y values were doing. What were they doing? Doubling, multiplying by 2 every time. Now, it doesn't have to be 2. It could be 3 or 4 or 5 or whatever, but it's got to be multiplying by the same number. So that's the first clue. So for tables, let me give you some information. For tables, I'll just make one up here. -1, 0, 1, 2, and 3. Let's say we start with, I don't know, we'll go 1, 3, 9, 27, 81. So what's happening in that table right there? What's going on from y value to y value every time? It's multiplying by 3. So that would indicate it's exponential data. So it's just like that one we looked at here. It's multiplying by 2 every time, right? So that would tell you that the general form, let me give you the general form. So it's when it's multiplying the same number, it's exponential. So that's how you would recognize in an XY table of data that it's from a function that's exponential if it's multiplying by the same number every time. So then they'll go, okay, you know it's exponential. Can you give us the equation? They'll ask us for the equation. So it's a times b to the x. That's your general exponential equation. Notice x is in the power zone. That'll be really important if you're going on to calculus. In calculus, you have a whole special way you need to take the derivative for exponential functions, which means x in the power zone. It's a special mark, and you got to do a special thing. So you got to know what they mean. So when your teacher, if you take Miss Wynn, she does a lot of it, a lot of the calculus teaching for us here. If you take her next semester and she says exponential functions, derivative is done this way, you'll know exponential means x in the power zone. It doesn't mean things like x squared. That's not exponential. That's just a polynomial. So, all right, so x in the power zone. So there's the general setup. Basically, the b is the number being multiplied. So in this case, the 3. So our equation becomes y equals a times 3 to the x. Good so far? So whatever that number being multiplied every time in the table, that's your b, that's your base. Now, how do we find the a? How am I going to actually find this a right here? A is always going to be the number right next to x is 0. That'll always be your a, which in this case is also a 3, coincidentally. Why? Well, because of the following power rules. I wonder, are you remembering the power rules from algebra? Let me review them real quick. Do you remember what, like a number to the 0, what is?
1.
Yeah, anything to the 0 power. Do you remember that that's 1? Doesn't that rule seem weird? Doesn't it seem like they just made that up? Like, why is anything to the 0 power 1?
It's got 0 power.
So why isn't it just 0? Or why isn't it just x? I mean, where'd the 1 come from? Like, you tell me that 17,516,318 to the 0 power is 1?
Yeah.
Good answer, Doug. Good answer. Yes. But why? Doesn't it seem like they just made that up?
Yeah, I mean, this was all made up.
Well,
That is not real.
yes, but what they let me be clear. They made up. What does it mean to put a little number in the upper right hand corner, like a 3? What does that mean? Does that mean 2 times 3 is 6? No. Yeah, that's a repetition symbol, isn't it? It's shorthand. It's lazy math people. They didn't want to write out all the 2's, right? Little numbers in the upper right hand corner mean repeat that many times. That they made up. Absolutely. They could have made little numbers in the upper right hand corner mean something else. But once they decided that little numbers in the upper right hand corner mean repeated, multiplied that many times, 8, then they perfectly, without flaw, without deviation, like a I'm losing my analogy. The bloodhound, following the scent of truth, followed it perfectly. So from there, logically, 2 to the 0 has to be 1. Now why? How could this, made up, lead to that has got to follow?
Because it's not times.
Think with me. I give you a couple of ways of proving that. I don't want to spend too much time, but I don't like saying things without reasons. So how about this? Just watch the pattern. What if you pick in here, instead of 2, we've done 2 already, let me go 5. What is 5 to the third? Well, that's probably too high. How about 3 to the third? Start with 3. What's 3 to the third? 3 times 3 times 3? 27. What is 3 to the second? 3 times 3? What is 3 to the first? Well, it's just 3. All right? Suppose I had no idea what's the next one in the line. Just follow the pattern. Math is just patterns. 3, 2, 1. What comes next? 0. Right? Just follow the pattern, okay? Now, suppose I don't even know what it is. Suppose I'm trying to figure it out. Follow the pattern. What's happening on the right side? What do they do? How do you...
Dividing.
It's dividing by 3 every time, isn't it? Dividing by 3. So divide by 3. 3 divided by 3? It's got to be. See that? It's got to be. To be consistent with the original rule, it had to be. They didn't have a choice here. They're not making... They made up this. This was made up. But once they make something up, they follow out what it implies logically perfectly. Math is a deductive field, which means it always takes an original thing and then just follows it perfectly without deviation. There's never a correction in math. You know that? There is in science. Science is inductive. I'm probably getting into too much stuff we don't have time for. But science looks out at nature or the world or our bodies or the skies and says, hey, this is happening. I think this is the rule. That's the best they can do based on what they've seen. But then over time, right, we see more. We have electron microscopes that are developed and see tinier things than we've ever seen before, or big telescopes. They're building a big one out in Hawaii somewhere, I heard, right? That's supposed to be done in 2020. That'll see even further than we've seen before. Anyway, they see more, and then they adjust their formulas because they're just based on what they see. That's inductive. They're inducing what they think to be true based upon what they've seen. That's the only way science can go. Math is deductive. So there's never a correction in math. Math teachers are never wrong. No, math teachers are wrong all the time. But math is never wrong. I don't know if you know that. There really is never a correction. Whereas science all the time, right? Newton thought things, then Einstein came along and went, no, near the speed of light, it's a little different, da-da-da-da-da. Math is deductive, which means we just take something, they make something up, and then they perfectly follow that. They never do anything that isn't 100% true, following what they started with. So, anyway, that's why anything to 0 power is 1. You can prove it other ways, too. I'm probably spending too much. Real quick, one more. I like little math. I like seeing the math is true. So, remember the rule with powers? Yeah, let me just give you those rules. Do you remember that, like, what if you have x to the a times x to the b? Remember that rule from your algebra days? You add the powers, huh? Yeah, that'd be like 2 to the third times 2 to the second is what? 2 to the fifth, huh? Now, why wouldn't it be 4 to the fifth? Doesn't it kind of look like that should be 4, right? 2 times 2 is 4. Why isn't it 4 to the fifth?
Because it's all just multiplying, shorthand for multiplying.
It's the same.
Well,
They're all twos.
yeah, they're all 2's. Yeah, what is 2 to the third?
It's
3 2's. What is 2 to the second? 2 2's. So what do you got there? 5 4's?
No.
We got 5 2's. Math is just follow the truth. See that? They're just saying, well, we agreed. Those little numbers mean 3 2's. That means 2 2's. What do you got there? You got 5 2's. See what I mean by that's deductive. They just follow what we originally assumed. So anyway, so what? Why am I doing all that? Well, we need those rules. We need to remember those rules. But also remember the other one. Like what if you had 2 to the third over 2 to the second? What's that rule? You subtract because that's 3 of them on the top, 2 of them on the bottom. They cancel, 1 left on the top. Remember the subtraction rule? Okay, so we're ready for a second way to prove that anything to the 0 power is 1. So what if that was 2? So again, one more time. What if it was, here, let me make up one even more interesting. What if it was 7 to the fifth over 7 to the third? What would that be? 7 to the second. Okay, now what if I changed it to third over third? What would the power be now? Same rule.
0.
It's got to be 0, doesn't it? I'm just following the same rule. I'm not making up new rules. And what is the same thing over itself? Always.
1.
So what does it have to be?
1.
There's another proof. Anything to the 0 power has to be 1. It's just the truth from the original assumption, isn't it? All right, enough with that. Probably too much of that. Do you remember what negative powers do?
They put
Gonna need to remember that today.
everyone.
Flip it. They flip it. Fraction powers root it. This would flip it, make it positive on the bottom. So we'll do a lot of this today. So negative powers, so remember that. That one's going to become real handy. In fact, I've got them on the board here for you. I think I put them in a different order. But there they are. One more. Which one am I missing? Oh, yeah. Last one. X to the A to the B. So if you have to the A to the B like that, they multiply. Let me get these out of the way here. They multiply. So there's the rules that you'll need to remember from algebra. And we'll be using a lot of these rules today. All right, let's get back to it. So where were we? Oh, yeah, so back to it. So we were trying to take that table and find the exponential equation that fits that table. And so we found out the number you're multiplying by times 3 every time. That's your base. And then how do you find A? How do you find A? Well, it's the number next to 0, huh? I was saying that didn't give you a reason. If you plug in 0 here, plug in 0 for x, you see what you'll get? A times 3 to the 0. And what is 3 to the 0? That's 1. So y is going to just be A. So that's why this is A. Whenever you plug whatever's next to 0 in the table, that's going to be the A. Because the power part just becomes 1. Anything to the 0 power is 1. Is that good? All right. Let's go back to the question then. I don't know if we have the... Yeah, there it is. So here is the question number 1. Let's take a look at those values on the right side. What's happening from 3 to 6 and 6 to 12? What's going on there? What's it multiplying by? It's going times 2. Times 2. Is it doing that all the way, though?
No.
No. Then it peters out right there.
Mm-hmm.
It's not. It should be 24. It's not. So this one is neither. This table is neither exponential nor linear. I know I haven't given you the rules for linear. I'll just say them. We'll see it in a minute. Linear is if you're adding the same number every time or subtracting. So this one is neither adding or subtracting the same number or multiplying the same number every time. It's neither. This one's a neither on that one because it's kind of doing different stuff. Let's go. Okay, so number 2 here. So number 2. So what's happening? So we want to look over there at the y values right away. What's happening from y value to y value? What's it doing every time? Times it by what?
8.
Multiplying by 8. Do you see that it's multiplying by 8 every time? If you take 1/8 times 8, the 8s will cancel and you'll have 1. And then you go times 8, it'll be 8 times 8 is 64. So it's just going times 8 every time? We good? So that means this thing is exponential, right? When you're multiplying, so it's multiplying by 8, so it's exponential. So it's a times b to the x, and the b is just your 8. Good to there? So the b is the number so the number right next to x is always the number you're multiplying by every time. And what's the a?
Just 1.
Yeah, remember the a is whatever's next to 0. That's a. In this case, it's just 1. We got it. There's the exponential equation that is producing that data in the table, those numbers in the table. You could check it out. If my test was on the line, I was taking this test, I would try it. I would plug in 2, 3, whatever, and see that it really works. If you plug in 2 there, you're going to get y equals 1 times 8 squared. Yep, sure enough, 64. It's working. Is that making sense? So that's the formula that is producing the values in that table. It's an exponential one. Okay, so there's number 3. See if you can, same thing, look over here at the y values. Use your calculator, those are big numbers. use your calculator, find out what's happening, see if you can write the equation. So what's happening from term to term there?
Times 11.
It's going times 11, huh? Because these 11s cancel. Times 11, times 11. So it's going multiply by 11 every time. So that means it's exponential, right? So it's y equals a times b to the x. The b is the 11. The number being multiplied every time. Good so far. And now, what's the a?
12.
Yeah, the a is the number next to 0. And we're done. You can check it. Plug in like 3. 12 times 11 to the third should be 15,972. Is that good? We okay? With going from tables to equations? All right. So here is number 4. Go over here, look at the y values. It'll be our last one. So you can figure out what's happening from y value to y value.
Just added 6.
Yeah, this time it's just, it's not multiplying, it's adding, huh? It's just adding 6 every time. It's not multiplying by the same number. It's just adding. What does that mean when it's adding or subtracting? Because you add a negative, that's subtraction, right? If you're adding or subtracting the same number, yeah, that's linear. Like a line, straight line. What's the equation of a straight line? Y equals mx plus b. Yeah, y equals mx plus b. So, mx plus b. Can we,
The slope.
yeah, what do you think the slope is? It's the 6. So the m is the number. M is number added each time. Why? Because that's, remember, slope is rise over run. These are the y values. How much y goes up is the rise. And the run is 1. They're only going up by 1 every time. So it's 6 over 1, 6. So that's the slope plus, now we need the b. How do we find the b?
Where x equals 0.
Yeah, it's going to be the same thing. It's whatever's right there. This time we're calling it B. Last time we called it A. Call it Joe, whatever you want. It's the number next to 0 has got to be your B, because if you plugged in 0 to your formula, see how if you plugged in 0 right here to your formula, then Y would just equal that number on the right. So there it is. It's linear. 6x plus 6. You could check it out. Plug in like 3. You plugged in 3 there. 6 times 3 plus 6. That'd be 18 plus 6, 24, sure enough. That formula is producing the values in that table. We good? So I'm going to leave this table stuff behind, if you're okay with that, and we'll go exponential graph. So how do they look? Y equals A times b to the x plus, I'm going to add another component now, plus c. And the c is the horizontal asymptote. So horizontal asymptote at c. So that means the number added or subtracted is the horizontal asymptote. Wherever that is the horizontal asymptote. And then the graph itself, what it does is it rockets up on one side and flattens out on the other. Exponential graphs always do that. They rocket up on one side, flatten out on the other. Notice how it goes up to the right. Have you noticed that we're adding to our toolbox? You see, remember we started with those original 6 graphs? Remember the snake and all the original 6, the absolute value, V, and all those, right? All of those, and now we're adding to it from here. Tomorrow, Thursday, we'll do logarithm graphs. We'll add another one. Today's exponential. All of them go up to the right originally, if there's no flips, huh? Have you noticed that? All of them originally go up to the right. So this one too, up to the right. So if you see one that's not going up to the right, you know it's been flipped somehow. If it's going up to the left, that means it's been flipped sideways. If it's going down to the right, it's been flipped down. It's going down to the left, it's been flipped down and left. Both flips, right? All right, so again, exponential graphs always flatten on one side, rocket on the other. Originally, upper right. Okay, so with that in mind, here we go. We're looking at an exponential graph, and they're asking us A, B, C, D, E, F, G, H. Which one of those is the equation to produce that picture?
Well, according to you, it's been flipped.
Yeah, let's talk about the flipped stuff. So has this one been flipped, or is it normal state? Yeah, it's going up to the left, isn't it? Normally, they're supposed to go up to the right. This one's going up to the left. So how has it been flipped? Sideways? Yes. Flipped sideways. Has it also been flipped vertically? No. Not flipped down. So it's been flipped left. We could just say left if you want, that helps. It's been flipped left and not down. So what does that mean? So what does that mean about the equation? What makes any graph, any equation, flip to the left?
Reflecting around the y-axis.
Let's don't talk about axis because that gets confusing in the x and y. Just what happens to the equation? Where do we put a negative? It's a negative sign, right? Negative on the x. Remember, because it's got to be an x effect, got to be a sideways effect, doesn't it? To make it flip to the left, got to have a sideways effect, negative on the x. What and not flipped down? What would make it flip down? So not negative on the front, because that's what makes things go down, huh? So we're looking for an equation that has a negative on the x and not a negative in the front, because that would make it go down. It's not going down, it's going up and left. So let's go through it. Could it be A? No, he doesn't have a negative on x. Could it be B? Yeah, he's got a negative on x. He's looking good. Maybe B. We'll keep going. Could it be C? No, he has a negative in the front. That would be down. It's not C. How about D? No, he's got a negative in the front, which would be down. It's not D. How about E? He doesn't have a negative on his x, so he'd be going to the right. He's supposed to go to the left. So no. F. Could it be F? No, he does not have a negative on the x. You got to have a negative on x. It's going left. No way. How about G?
Maybe. There's a negative x.
There is a negative on the x. So he's a candidate too. He's running for election also. H. Could it be H? No, he's got a negative in the front, which would make him go down. And no negative on x. So we're down to B and G by the flip talk. We good? So far so good? How are we going to determine if it's B or G? What do I always suggest you do at the end of these if you have two options? Table. Table. So I'm going to get rid of this stuff and make a table now. So yeah, so I'm going to try out B first. So let's do that. So trying out B. So I'm going to go X, Y, and try B, 7 to the minus X. Okay, so what should I plug in? What would be the easiest point to plug in? 0, right? Plug in 0. Y equals 7 to the minus 0. Minus 0 is just 0. What's 7 to the 0? 1. So over 0, if this is really the right thing, the right equation, then over 0, up 1 should be a point the graph hits. Here it is. Here is the point. Over 0, up 1. Does the graph hit? No. It's not B. Right? This is over 0, up 1. The blue graph is not going through that point. All right, let's try G then. And I know you're probably thinking, well, it's the only option left. It's got to be G. Right. But on my test, there's always the none of the above, so let's make sure it's really G. So what am I going to plug in? Write this out here. 7 to the 1 minus x. What am I going to plug in? What would be the easiest thing to plug in? No, are you getting the hang of how I say to find the center?
Oh, wait, you have to make the center 0.
You've got to make the x world 0. Are you tracking with me? What's x's world? Right here. 1 minus, what are you going to plug in for x? 1. Does everybody see that? Can you see that okay? Right, you always want to make x's little world. What do you mean his world? Like if he's in the power zone, if he's in the absolute values, if wherever he's at, wherever he lives, go into his shoes and make his world 0. That's the easiest point to find. That's the center point. So I'm going to plug in 1. See, in the last one, he was just 0. Right, he didn't have any other numbers up there with him. Here I'm going to plug in 1. I'm going to get 7 to the 1 minus 1. 7 to the 0. 1. So 1, 1. So if this is really the graph, then 1, 1 better be on that graph. Is it? There it is. Perfect. 1, 1 is a point the blue graph goes through. Yeah, G is the right answer. We good with that? So see how we eliminated everything but 2 options from the flip talk. We knew it had to have a negative on the x and not in the front because it was going left and up. And then we got down to 2 options. We made a table for both of them. Found which one had the right dot. Questions on that? Okay, so try number 6. So decide, the general a times b to the x plus c. So try the flip talk. Think about how's it been flipped and what does that mean about the equation. So how's it been flipped? Has this graph been flipped? It looks like it's going
Just down.
down and right. So normally they go up and right. This one's going down and right. So how's it been flipped? Been flipped down. Not sideways though. It's not going left, is it? It's right down. So it's been flipped down. And what's going to do that? Negative in the front. Not a negative on x, huh? So we're looking for a negative in the front and not on x because it's going down and right. So let's go through it. Could it be A?
No.
No negative in the front. Could it be B?
No.
No negative in the front. Could it be C? Possibly. It's got a negative in the front. Could it be D?
No, because of the x.
It's got a negative in the front, but it also has a negative on x. That would make it go left and down. It's not going left and down. It's going right and down. No. How about E? No negative in the front. No. F?
No.
No negative in the front. G?
No.
This is easy, huh?
H for sure.
H?
Yeah.
Negative in the front. Okay, so we have 2 candidates running for election again. C and H. It's going to be one of those.
Well, okay, so does C have an implied?
Yeah, so you guys, Abdul and Renee, you're right on the money. Yeah, let's think about, we can skip the table stuff here. If we'll just think about the horizontal asymptote. Yeah, remember what we said. Remember what that C is? The C, the number added or subtracted, is the horizontal asymptote. What is, look at the graph. See what the horizontal asymptote is? 1. So we got to have a 1 out here added, don't we? See, it's H. If it bugs you, you could put that 1 in the back. It's the same thing, right? Minus 7x plus 1 or the 1 in the front, whatever. H is the right answer. No way is C right. He doesn't have a 1 out there. He needs to because there's a horizontal asymptote of 1. So we don't even need to make the table. H has got to be the answer. It's the only one with the right horizontal asymptote, and it's got the negative in the front, flipping it down. Are we okay with that? Not making sense? Okay. So, all right, so they're giving me the equation y equals 4 to the x minus 4.
That's its B.
And we're going to try to think about which equation is right.
B.
So what is this minus 4 right here? What does that do? What is that?
It's something that it can never cross.
That's the horizontal asymptote, right? Remember, the number added or subtracted is the horizontal. So that means this graph at down 4 has a horizontal asymptote, huh? Which means, remember, that's where it flattens out. So exponential graphs always rocket on one side, flatten at their horizontal asymptote on the other side, which means they get closer to it forever. So which graphs are flattening at down 4? We're done. That's all we needed. That's the only graph that levels off at down 4. Huh. This one levels off at 0. This one levels off at 0. This one levels off somewhere up 4, looks like. Good? All right. So y equals 3 times 1/5 to the x. What do you think? I'm gonna present some reasoning, which is crazy, but it's sure sounds good. You tell me what's crazy. Let's talk about flips. Are there any negatives anywhere? First off, what's the horizontal asymptote?
Here's one.
There, it's plus 0, so the horizontal asymptote should be at a height of 0. Should level off at a height of 0, right?
So you can get rid of C.
So we can get rid of C, because that one's leveling off somewhere other than 0. Good so far? I like to just eliminate things right off the bat. Good. All right, now let's talk about flip talk. Are there any negatives anywhere?
No.
No negatives anywhere. So that means it's not been flipped, right? So it should go, so where does it go if it's not flipped? Up to the right.
Yeah.
So that would be A, and we're done, and I'm wrong. That's not the truth. So what's the story? I can tell something you want to chime in. What's the story?
So you have a fraction.
Yes,
So
which,
it's divided. So
okay.
It's a number divided, so it's a flip, right?
It's a flip. So what does that mean about the power?
Negative exponent.
Negative power. Very good. Yeah, they're sneaking a negative on us. That 1/5 is 5 to the minus 1, remember? Go back to the power rules. Where are they? Somewhere. Here. Remember, negative powers like 5 to the minus 2, for example, is 1 over 5 to the positive 2. Negative powers flip. Fractions are negative powers. That's the curveball. They're sneaking it in on us.
Don't move
Like me or the screen?
the screen.
I'm just kidding, Doug. How about I just write it over here? Okay, so I thought maybe there's a big spider on my back or something. Don't move. I'm sorry, I'm still just kidding you.
Might be.
All right, 5 to the minus 1. Yeah, do y'all see that? 5 to the minus 1 is 1/5. Negative powers flip things. So that's the trick they're sneaking it in on by putting a fraction there. So then what do you do with these two powers?
Add them. Multiply.
You multiply them. You multiply them. Yeah, so are we good so far? So then, yeah, and then the power rule with the, when you have one base, two powers multiply, don't they? So that would be 3 times 5 to the minus x, right? That minus 1 and x multiply. So we do have a negative power, really. Right? We have a negative on x. And so what does that mean when you have a negative on x? Sideways, right? It's going to go left. Your left is that way. Left instead of right. So it's not A. A is going to the right. So it's either B or D. B and D are both going up left, up left. They're both flattening at 0. They both look good. What I got to do?
I would say it would be
Table time, right? Everybody with me as far as we're down to B and D? Because we have a negative on x, which means you go left, up and left, and the horizontal asymptote is 0, so that's good. There's no number out here, plus 0, you know. So we got to do the table for those two. So let's go do that. Let's do the table. So let's start, let me just make a table here. So let's go x, y. Y is equal to 3 times 5 to the minus x. So what should I plug in? 0, right? I want to put in a 0 right there because that's what will make that world 0. 3 times 5 to the minus 0, that's just 0. And that's 1. 3 times 1, that's 3. Over 0 up 3 should be the center point of the graph. Let me see how I got that? So let's take a look. Over 0 up 3, yeah, that looks perfect on the B graph. Over 0 up 3 misses on the D graph, so it's B. We good? So watch out if they try to sneak a curveball. A fraction is a negative power. They're testing if you know that. Fractions are negative powers. Good? I'll move on if you're okay. Okay, so here we have y equals 5 minus e to the minus x. So do you know that e is just a number? First off, I put it up here on the board as well. E is just a special number. It's 2.718, blah, 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 blah. Just like pi is a special number, 3.14, blah, 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 blah. So e, first off, e is just a special number. What it is, why we have that special number, you'll learn more in calculus. It's a special calculus number. It's the perfect number who's his own derivative. That's what it is. It's the exact number who is his own derivative. Anyway, you'll learn more about that in calculus. For now, we'll just say, hey, it's a special number. So it's just a number, just 2.7 whatever, whatever. And like pi is 3.14. So it's just normal, really. So we're just going to graph this thing like normal. So here we go. So just pretend that's a 2, for example. Well, that's what I'm saying. So don't think you need to do anything real amazing. You don't. Just pretend that's a 2 or a 3 or whatever. So what would you do if that was a 2? You would just say, okay, need to graph it. Let's start thinking about the graph. What's the do we have a horizontal asymptote? Yeah. What's the horizontal? It's that 5. Are you okay with that? If it bugs you being written that way, you could always rewrite it this way. You could put the 5 off to the right. You don't have to. But if that helps you see it better, this is the E really, then great, feel free to do that. That's the same thing. So the 5, that's the horizontal asymptote. So the real graph has a horizontal up at 5, doesn't it?
Yeah, but I think it's going to be flipped because, well,
yeah, and then we'll talk about flipping. But so first off, which one is gone already? Which one doesn't flatten out up at 5? Bye-bye A. He's flattening out low. So the other ones all flatten out up at 5. Flattens, flattens, flatten. They're looking good so far. Yeah, now let's talk about all the flip talk. Right? We have a negative in the front here and a negative on x. We're double flipping. We're going down and left, aren't we? Negative on the x flips it left. Negative in the front flips it down. Which one is going down and left?
D.
D. Down and left. We're done. We good? Right? Because C goes up and left. B goes down and right. D is down and left.
In this case, the first thing that we're going to do, the first down, then flip it.
Oh, yeah, I can go. If you want to talk more about that, I can grab you in office hours. But generally, all we need to know is the direction. So it's going to go down and it's going to go left. Okay, so now we've got y equals 3 plus e to the minus x over 2. Again, e is just a number. So this will actually be a pretty easy problem. First off, what's the horizontal asymptote?
3.
3. Positive 3, right? There's the horizontal. So which of these are flattening out at up 3? Or who's out?
B.
Yeah, B, huh? B's out because he's flattening out somewhere negative. That's not right. The other A, C, and D are all flattening out up at 3. So they look good so far. Okay, now, let's talk about the flip talk.
Fractional exponent.
What's the negative? I won't even worry about the fraction right now. Just what's a negative on X?
It's gonna be a side,
It's going to flip it
sideways.
left. Sideways left. Instead of up and right, it's up and left. Right? And there's no negative. This is positive in the front, so it's still going to go up. So we're talking up and left. Which of them go up and left? A it is. We're done. That flip talk really helps. You guys okay with all the flip talk? Is that making sense? So the sign in the front, positive is up, negative is down. The sign on X, positive is right, negative is left. It's nice that these exponential graphs just go one way and the other side flattens. So it's easy to spot them. Looking at equations. How do you handle X's in the power zone when it comes to equations? Exponential functions when it comes to the equations. They want to know X there.
You get rid of it with a log.
Later.
Oh. Darn it.
So what do you think 4 to the X equals 4 to the 5th?
Well, then X equals 5.
Isn't that great? I mean, like, if you were to tell somebody, how'd you solve that? Like, what technique did you use? What method? Did you get a 0? Did you factor? What would you say?
I just looked at the other one.
I matched.
Yeah, match. That's good. Match them up. How about this? By clear observation. That's called solving by observation. I always think that because when I was in grad school, my last quarter at Cal Poly, I took this one class, and it was super, super hard. Well, the book was super hard because my professor, Dr. Baser, she used the book from her professor from UC Santa Cruz that she'd taken, Dr. Whittam, who was too smart to write books and be a teacher because he was so smart that he didn't know how to explain it to dummies like me. He wrote this book, and she thought it would be fun to use the book that she had used for us, who were her graduate students at Cal Poly. And so I remember reading the book. It was a course called Measure Theory. And he had in calculus, you learn about integrals. It looks like a big S. It really is a big S. That's what it is. Anyway, he had this one crazy statement, these integrals and these limits, something else you do in calculus. He had these limits everywhere. It's something else called the soup. It looks like soup, but it's some special math thing. And blah, 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 X's everywhere. It's crazy, crazy, crazy. And then all he wrote, to explain, he just wrote, by clear observation, and then he wrote equals 3.
Wow.
And I remember went, by clear observation? Are you kidding me? Whose observation? Not my observation. I'm looking at it. I remember I spent hours of my life, literally, more than a day, working on this, trying to do the thing out to find out how it equaled 3. I went to my teacher's officer, Dr. Baser, and I said, how is this 3? You know, and she worked stuff for me, and I still didn't get it. It was hard. And I remember saying to her in kind of a frustrated tone, saying, there was only like 10 of us in the, there's not that many students in the class, like 10 of us that were in the program. And so we all knew each other, we were all talking all the time. So I knew nobody was understanding this, you know. So I said to her, do you know, nobody can read this book. Nobody understands this book, probably with that kind of a tone too. And I remember she just laughed. She went, ha ha ha, I know. Yeah, and she just thought it was funny that nobody could read the book. Anyway, so that became our joke that last quarter of grad school, by clear observation. So anytime one of our professors did something crazy hard on the board, we would all look at each other and go, by clear observation. Clear to the most casual observer. Just a passerby would go, oh yeah, there it is. So there we go. So this one is true by clear observation, even for normal folks. That's true. Let's try the next one. Let's try number 16.
You cannot go by law.
Go by what?
Like,
Later. Thursday. Yeah. So try that one. Can you solve that one by observation? I'll give you some techniques in a minute. But if you could just look at it, great. Can you tell what does X have to be? What do you got to put in right there?
-2.
Good observation. Do you see that? Because negative 2 will become positive 2, and 3 to the 2 is 9.
Oh, it doesn't need to be a fraction.
Right? 3 to the minus, and if you plug in minus 2, is 3 to the 2 is 9. The double negatives cancel. If the negative stayed, it'd be a fraction. But you want the negatives to cancel because this is not a fraction. Good? Can you solve that by observation? So observation is different for every person, huh? If you're like, Whittam had his PhD, not his bachelor's degree, his PhD by the time he was like 24, 25, 23, 24, 25. I didn't have my bachelor's degree until I was 24. He had his doctorate already. He was like a genius boy. He was too smart to write books. That's why he did crazy stuff like that and said by clear observation. Because it was clear for him, but not for normal human beings. Anyway, so how about number 17? Can you solve 17 by clear observation?
No.
Just look at the top. 2 to what power is 8?
3.
3.
X has got to be 3, huh?
5 times 5 times 5 is 1.
Yeah, 5 times 5 is 25. Times 5 again, 5 quarters. How much is 5 quarters? $1.25. Yeah. That's probably about the limit of our clear observation ability, about right there. I'll show you technique in a second. We're not going to do them all this way. Is that good to there? You okay with those observations? So I'll write it bigger. 2 to the 2x plus 1 is 4. What do you got to plug in for x to make that true?
1.
1 over 1 half.
What is it?
1/2.
It's a half. You see it? If x is a half, then 2 times a half is
1.
1 plus 1 is
2.
2. 2 to the 2 is... Yeah. Now, I'm going to show you a method at this. At this point, I'm assuming we can't all do that. Right? So let me give you a way to solve it when you can't just look at it. So this is what I wanted Whittam to do for me, but he was too smart for that. So 2 to the 2x plus 1 is 4. So how do you solve these things when you can't just see it? So when x is in power, that's what we're talking about, right? That's what exponential means. X is up in the power zone. What do you do? Step 1, you make the bases the same. You make the bases become the same. So what do I mean, make the bases the same? Well, this side is 2 to the 2x plus 1. I want to make that 4 become 2 to some power. What is it? 2 to what power is the same as 4?
2.
2 squared. See, now I've made the bases the same. That's still a 4 over there, right? 2 squared is still 4. But now I've made the bases both the same. That's step 1.
2x plus 1 equals 2.
Yeah. Step 2, powers are equal. These, once you've made the bases the same, then you can say the powers must be equal and you can solve it. Why? Well, because if the bases are the same and you have equality, the powers must be the same also. If they were different, then 2 to one of them wouldn't equal 2 to the other one. If those powers were different, if those powers were not equal, then 2 to one of them wouldn't equal 2 to the other. Since they are equal, you know those powers must be equal as well. Right? Then just solve. Subtract 1. 2x is 1, divided by 2. There's the answer that some observed. X is a half. That's all I wanted Whittam to do for me. Save hours of my life.
Yeah, I'm never becoming a math teacher.
Whittam would just say I had no business reading his book. I'm sure that's true. I'm way out of his league. So, we good there? Not making sense? All right, so let me rewrite that one for us. So,
Oh, yeah. I love how
4 to the x squared is 64 to the x.
what you can buy in addition to your textbook.
Okay, so try that one. So you know the game plan, right? Make the bases the same. So just use your calculator. That 64 is 4 to some. Don't say it out loud. Give everybody a chance. Just take your calculator. Just take 4 and just start multiplying until you get 64. Then you'll know what power you need on the 4 there. Make the two bases the same, right? I'm assuming this one's too hard to do by observation. So step 1, make the bases the same. So take your calculator, go 4 times 4 times 4. It's 3 of them, isn't it? We good? 4 times 4 times 4, 3 times is 64. So that's step 1. I made the bases the same. Step 2, powers must be equal, right? Because if they were different, right, we have equality. So if the bases are the same, the powers have to be the same also, or we wouldn't have equality there. So go ahead and set those powers equal now, and solve. So solve x squared. So it's all come down to solving x squared is 3x. So I'm hoping this is becoming more and more comfortable for you. How do you solve x squared whenever? Because we're going to see this a lot. This wants to become really, really comfortable, like an old pair of shoes. What do you do when you see x squared? Get a 0. You want to know immediately, get a 0. So whenever you see x squared with it, let me write it out again. Get a 0 and factor. That's always the game plan. Whenever you see x squared, it's going to come up throughout the whole semester all the time. Same thing in calculus. Just get a 0. So jump this over. So we'll get x squared minus 3x 0. Factor, how do I factor that? Take out an x. So what'll make that 0? 0. What'll make that 0? 3. 0 and 3 are the answers. We are done. So once there's 2 answers this time. Both answers with a comma. 0, 3. You could check it out. It's true. 0 we should have seen, huh?
Yeah.
Hitting the 0 power is 1. Of course. 0 works. 1 equals 1. 3 also works. Are we good there? Is that okay? You guys, was this too short how I solved that? Bless you. Right, I just said what'll make that 0, what'll make that 0. Right?
So, sorry, the top part where you're going from 64 to the x to 4,
Right there.
you're
I'm making the bases the same.
making the bases of
So I saw him as a 4. I thought I got to make 64 be 4 to something.
Okay.
So how many somethings? Turns out 3. I just took my calculator. 4 times 4 times 4. 3 times is 64. So I'm making the 2 bases be the same. So I'm making the bigger base become the same as the smaller base.
Oh, okay.
But that's still 64. 4 to the 3rd is still 64. It's just written with the same base as the other one now. Is that good? We okay with all that? Okay, so try that one. They want you to solve for x. So you know the game plan. Make the bases the same. Make the bases the same, and then you can set the powers equal. Use your calculator. So 81 is 3 to the 4th, and 27 is 3 to the 3rd. All to the 5x on the left side, all to the x plus 1 on the right side. Good so far? I just made them both have the same base. Now we've got to remember the power rules. So what do these powers do? When you have one base, 2 powers on the same base, they multiply, don't they? So that'll be 3 to the 20x. And these powers multiply. 3x plus 3. We good? So that's step 1. Base is the same. So now step 2. Powers equal. So the powers have to be equal. Like that. Solve for x. Right? Because if these things are equal and the bases are equal, the powers have to be equal too. Or they wouldn't be coming out equal. 17x is 3 divided by 17. Now why didn't one of you observe that?
I did.
From the beginning. It was just clearly 3/17. Clear to the most casual observer. Just a passerby. Just walking by our room. We just look in and go, oh yeah, that? 3/17.
I would kick them out of here.
I'm sure that's how Whittam worked. All right, good on that. Questions? on that one? We good? Okay. Same thing. Make them both the same base. What base could you make both these?
3.
You could do 3 again, but there's
Should do nine.
you could do 9. That'd be easier. 9 would be a little, either one will work. Either one will work. 3 or 9. But since one of them's already 9, it'd be quicker to just do 9. See, last time we couldn't do 9 because 27 is not 9 to some power. Right? 9 squared is already 81, it's already bigger than 27. But this time, yeah, you can do 9 for both those. So this is 9 squared, huh? 81. Is that good? See how I made them both 9? And then these guys multiply each other. We good to there? So step 1, bases the same. Step 2, powers equal. So now these powers have to be equal because we have equality. If they were different, 9 to one of them wouldn't equal 9 to the other. They've got to be the same powers. So now how do you solve? Once you see x squared, what's always the game plan?
Get a 0.
Get a 0. So jump this 6x over here. Get x squared minus 6x minus 7. You always get a 0 first off. And then factor. Remember how to factor that? We're looking for two numbers that multiply to be minus 7, add to be minus 6. What times what? So 1 times 7,
Negative 7 and 1.
negative 7 plus 1, because that'll make negative 6, right? And they'll multiply to be negative 7. So then what are the answers? You know it's just going to be
Negative 1.
negative 1 and positive 7. It's always opposite, right? Is that okay? I just skip that? Right? If you made x negative 1, that would make that part 0. If you made x positive 7, it would make that part 0. Right? And that would therefore equal 0. So there we go. Negative 1, positive 7 are the two answers to that exponential. Good? Getting the hang of this? Make the bases the same, powers equal. No questions?
Yeah.
You guys are a group with very few questions. I'm glad to answer them. You all good? Renee, you can solve that by observation, right?
Oh, clearly.
All right. So make those bases the same. What base should you work with?
6.
Yeah, they're all, you can do 36, that's 6 squared. 1296 you probably don't know, but try it in your calculator, multiply a bunch of 6s, you'll see it comes from 6 of those. Yeah, so make it 1 6 on the left side, 1 6 on the right side. Make the bases the same. Then you can set the powers equal and go from there. Okay, so 36 is 6 squared.
6 to 1.
And 1296, is that 6 to the 4th?
Yeah.
No, it's not 5th, it's 4th? Squared. We good to there? And then, remember, these guys multiply, so this is 6 to the 2x. 6 is, these guys multiply, 6 to the 8. Now, are you good with those power rules? Here they're testing both power rules. Gets a little tricky. See, these are two separate bases. So what do the powers do in that case?
You add.
Add 2x plus x squared. Everybody see the difference? See, like up here with the 6, 4, 2, that was one base, 2 powers multiply. Right? But if you have 2 bases, powers add, don't they? Remember those different rules are still, I gave them to you earlier. Basically, x to the a times x to the b. 2 bases, powers add. But if you have 1 base, 2 powers, that's when they multiply. You good with those 2 different rules? You want to be really clear on those. That's so much of pre-calc and calc, is really just mastering the rules that were given to you in algebra. They were given to me when I was in algebra, but I was not nearly at all a master until I'd finished calculus. That's kind of what happens for most people. So that's a lot of what this journey is about, is mastering those rules they gave us back in the algebra days. Is that good? Remember those rules? See how we're applying those here? So that's step 1. All that's step 1. Base is the same. Base is the same. Now step 2. Powers equal. Oops. Come on. Powers equal. So grab these 2 powers and set them equal. So 2x plus x squared is 8. Right? Can I just go dot, dot, dot? I'm getting a little tired of solving these. There's big stuff we need to look at.
Negative 4 and 2.
Get a 0, what it is, negative 4 and 2. Get a 0 factor, blah, 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 blah.
I could be wrong.
I'm sure you can all figure it out. Is that good to there?
Clear observation.
Yes. It's the big one. So, e to the x squared equals e to the 7x times 1 over e to the 12. All right, well, the base is clearly e, so we want to just make it 1 e on the left, 1 e on the right. So can you do that? So try that. Make it 1 e on each side. The left side already is, not much going on there. Oops. Yeah, what do you do with this 1 over e to the 12th? Yeah, remember, negative powers. Flip, huh? So they're testing that again. That's e to the minus 12, isn't it?
Oh, I was reading wrong. I thought that was supposed to be like an exponent with the 1 over 12.
Oh, I know that bar went all the way like that. Okay, so that's that. And now on the right side, so we have e to the x squared equals. Now, two separate bases. Powers, add, subtract, 7x minus 12, huh? And then, from there, now,
Get a 0.
set these powers equal. X squared, 7x minus 12, dot, 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 get a 0 factor. Is that good? Is that okay? Getting the hang of all those power rules? All is well? All right, I'm going to move on. Okay, so they're saying 7 to the x is 4. I don't even know what x is.
Yeah.
And then they're saying, hey, if you know that 7 to the x is just 4, could you find 7 to the minus 2x? What would you need to do to this guy to make him look like that?
Times it to the negative 2 power.
Yeah, do the negative 2 up in the power, right? You with me? Right, if I took this guy and I did negative 2 in his power, he'd become that, wouldn't he? You with me so far? I'm just kind of looking, going, well, they're asking me about this, so I got to make this look like that. Right? I just got to make it look like that because that's what they want from me. It's kind of a weird thing they want, because normally they want x. They're not asking for x. They're asking for this weird 7 to the minus 2x thing. So I'm just looking at what I started with, saying, well, to make this look like this,
So you
I just got a minus 2 power. But if you do that to one side,
do it to the other.
you have to do it to the other. Right? If two things are equal, you treat them the same, they'll be equal when you're done.
20.
So what's that gonna do? Is everybody good with that so far? Right? So I'm just looking at that 7 to the x, saying, well, to make it 7 to the minus 2x, I'm gonna have to negative 2 power it. Then I gotta do the other side also. Now what is 4 to the negative 2 power?
1/16.
Yeah, what do negative powers do?
Fractionate them.
Flip, they fractionate them. I've never heard of that before. The fractionator. So 1 over 4 to the positive 2, right? Negative powers jump, then become positive. I always tell my algebra students, my teachers, they're unhappy. They're negative. They're unhappy at their job. They want to jump to a new job. After they jump, then they're happy. They're positive. So if that helps. So negative powers jump. They're unhappy. They jump down to the bottom. And then, that's 1/16. We good? See what I did? I just looked at the original and said, oh, you want me to make them look like that? Okay, I got a negative 2 power it. So I had to do the other side also. Try that next one. Number 26. Here's the original. What do you got to do to it? Don't say it out loud. Give everybody a chance to think about it. What do you got to do to it? See if you can figure that out in your own paper there. What do you got to do to that 8 to the minus x thing? That's how it starts. What do you got to do to it to make it 8 to the positive 2x? So what do we got to do up there? Negative 2, huh? Again, because negative 2 times negative x will be positive 2x, won't it? Whatever do to one side, got to do to the other. We already know what that is, right? That's 1 over 13 squared, 1 over 169.
Fractionation.
We good? I think we're close to being done with this section. I think there's one more and we're done. I mean, there's only one more I'm going to do. There's some others, I think. But all right. Okay, so this time they're giving me a graph. This is number 28. And they're giving me a graph, and they want me to work backwards to the equation. All right, so I skipped 27. I want to do this one first. So how do you work backwards? Well, that's clearly exponential. It's flattening on one side, rocketing on the other. Exponential. Yeah, it's been flipped. So it's a times b to the x plus c. That's the general setup of any exponential equation. What's the c? C is the horizontal asymptote. Yeah, that's 0, right? Isn't it? It's flattening. The dotted horizontal asymptote must be 0. It's flattening out at 0. So that part's just 0. So it's a times b to the x plus 0. You good so far? Okay. Now, what's the b? That's the weird part. Let me help you with that. The b is really the main thing. The b is the base. It's what has the x on it. It's the main thing that's happening. So I'm going to encourage you to figure that out by just taking a broad angle look.
Clear observation.
Yeah, clear observation. By the pattern. Just look at those numbers. What number do you see a lot of? Yeah, 1/4. That's a 4 flipped. 4, that's just a 4. Don't worry about the negatives and the other stuff. 16, what's that? 4 squared. Now this one, 0, 1, well, that's because at 0, anything to the 0 power is 1. That's why he's always going to just be 1 or negative 1 or whatever. But the other guys all seem to have some kind of a 4 thing, don't they? Your base must be 4. It's all about 4. They're doing something with 4 everywhere. Okay? Now all we got left to find is A. We good to there so far? So you just look at what number they're all operating on. 4, right? 1/4, 4, 16, 4 squared. They're all doing something with the 4, other than the 0, 1 or 0, negative 1, because, anything to 0 power is 1. So anyway, now we're down to just needing the A. We found the C is 0. The B is 4. So the C is the horizontal asymptote. That was 0. It's flattening at 0. The B is the number they're using repeatedly. That's the 4.
The A is whatever's next.
How do we find the A? Yeah. How do we find it? Yeah, it's the number next to the x0. Remember that earlier from the table work? That's it. So negative 1 times 4 to the x. There's our formula. And that makes sense because that's what does a negative 1 in the front do? Flipwise. Flips down. And that's what this one is. This one's down and right, huh? Negatives in the front, not in the x, but negative in the front flips it down. It's all perfect agreement. What we've learned about graphs, what we've learned about tables, what we've learned about equations. Perfect fit. Right? Right, good? How we doing? You guys got 15 more minutes of so 21, 31. Did I say 21? 31. This is a super easy question, actually. Just hit buttons on your calculator. See what there's. Here's the formula. Let me write it a little bigger for you. The P formula is 20,901, 0.92 to the x.
Is that your equation?
The x is the years old. And they're saying on question, I don't even need the rest of the words. Question A, how much does a 3-year-old car cost? 3 years old, x is years old. They're saying take that 3 and plug it in right there for x. Be 20,901, 0.92 to the third. Hit the buttons on your calculator. Answer goes right there. Part B, plug in a 9. Hit the buttons on your calculator. That's a depreciation formula. If you're interested, we'll go, and yeah, in week after next, after the test, next section, we'll be doing financial. We might even start next week. The financial stuff, so you'll get used to this. 20,901, that's the original price of the car. And 0.92, that means it's an 8% depreciation because it's 8% below 100. Yeah. So it loses 8% of its value every year. That's what that basically is doing. So it's 20,901 car, you're losing 8% of its value every year.
It loses like 8% of its value when you drive it off the lot.
Yeah, it's true, huh? All right, I'm done with that section.